picture a Cessna 172 sitting out on the tarmac. Just as the sun is coming up, you see the pilot walking out, doing a quick walk around, tapping the wing, checking the fuel. It really looks like the start of an adventure. It's this very romantic image we have of flying.
Right, yeah.
But the reality is that flight didn't actually start right then. That flight started, I mean, weeks, maybe even months ago in a loud, brightly lit hangar long before that pilot ever touched the door handle.
Exactly. I mean, we tend to focus entirely on the person sitting in the left seat. The pilot gets all the glory. But the absolute bedrock of aviation is that, well, the person holding the wrench is every bit as important as the person holding the yoke.
And that is exactly our mission for this deep dive today. So whether you're, say, a high school student eyeing your future career, or just someone who looks up every time an airplane flies over, we're unpacking the hidden world of aviation maintenance.
Oh, yeah. It's a deep world, too.
It really is. And we have a massive stack of sources today to guide us. We're pulling from the FAA's regulations, specifically Parts 43 and 91, the Aviation Instructor's Handbook, various FAA safety briefings. And we've also got global talent forecasts from Boeing and CAE, plus wage data from the Bureau of Labor Statistics.
So for this conversation, I want you to look at all of this through my lens. I'm stepping into the boots of a master airframe, a power plant mechanic, an AMP.
Right.
I've spent 30 years keeping the general aviation fleet airworthy. Everything from, vintage metal planes to modern glass panel jets.
Yeah.
And I want to show you the high-stakes, kind of gritty reality of what it actually takes to keep these machines safely in the sky.
Let's start right back on that tarmac then. The pilot is doing their pre-flight assessment, and the instructor's handbook mentions they're looking for things like wingtip cracks or something called black oxide film around the rivets. Mechanically, what is actually happening to create that film?
Well, when you look at the aluminum skin of an airplane, it's held together by hundreds of solid rivets.
Yeah.
And over time, from the intense vibration of the engine and just aerodynamic stress, a rivet can get slightly loose in its hole.
Okay, so it's wiggling around a bit.
Exactly. And as the aluminum skin rubs against that loose rivet, it shears off microscopic particles of metal. Those particles oxidize almost instantly in the air, and that creates a fine, dark soot.
Oh, wow.
Yeah, that is the black oxide film. It actually looks like the rivet is smoking, so it tells the pilot right away there's a structural compromise in that joint.
That's an incredibly clever diagnostic. But it also feels, I don't know, very surface level. The pilot is just assessing the exterior, making sure it's safe for a flight today. But the real deep dive, the actual structural reset of that aircraft, that happens during the 100-hour or the annual inspection, right?
Oh, absolutely. The relationship between the pilot's pre-flight and the mechanic's annual inspection, it's entirely symbiotic. According to FAA Part 43 Appendix D, an annual inspection is invasive. I mean, we are taking things apart.
Like a full surgical workup with an MRI?
Basically, yeah. We remove access doors, the fairings, cowlings. We expose the literal bones of the machine. The regulations actually require us to thoroughly clean the aircraft and the engine before we even start looking at it.
See, it's fascinating that the regulations literally mandate a wash before an inspection. It kind of implies that grime is treated as a physical barrier to safety, not just, an aesthetic thing.
Exactly, because you cannot see a hairline fracture in a crankcase if it's covered in baked-on oil.
Right, that makes sense.
We're looking for things a pilot could never possibly see on a walk-around. We check the flight control cables for internal fraying. We inspect fabric deterioration, look for structural distortion. We are physically pulling components apart to ensure they won't fail.
Which brings up a huge issue of trust, I'd imagine. I mean, how does a mechanic build trust with the pilot when the pilot can't see 90% of the work you just did inside the engine cowling?
Yeah, trust is everything.
Right.
And in this industry, there is a lethal danger in what the safety briefings call maintenance norms. Yeah, doing things the way they've, quote-unquote, always been done on the hangar floor instead of what the manual actually says. Or, even more dangerous, pencil whipping a logbook.
Pencil whipping? That sounds bad.
It is. Pencil whipping is when a mechanic signs off on a maintenance record, legally declaring they completed a task, but they didn't actually do the work.
Yeah.
In aviation, I mean, that is a literal death sentence.
One of our sources, the FAA safety briefing on combating maintenance norms, it highlights a pretty chilling historical example of what happens when procedures are bypassed like that. The crash of American Airlines Flight 191 back in 1979.
Yeah, that was a tragedy. That was a DC-10. So mechanics were performing maintenance that required removing the engine and the pylon, which is the part that attaches it to the wing.
Right.
The manufacturer's manual specified detaching the engine first, and then the pylon, in this very careful, step-by-step sequence. But a maintenance norm had developed. The mechanics figured out it was, well, quicker to just use a forklift to support the entire engine and pylon assembly and detach them together.
Wow, so they just bypassed the manual to save time.
Exactly. And during the procedure, the forklift's hydraulics slowly leaked. Over the course of the maintenance, the forklift drifted down about 1 inch every 30 minutes.
Oh, no.
Yeah, that slight unintended drop applied immense leverage and pressure to the engine pylon, and it caused a fracture in the structural flange. And it was a crack nobody saw because it was hidden away inside the assembly.
Because they didn't take it apart the way they were supposed to.
Right. So on May 25, 1979, during takeoff from Chicago, the aerodynamic stress completely overwhelmed that damaged pylon. The engine ripped entirely off the wing, tearing through the hydraulic lines. 271 people on board and 2 on the ground lost their lives.
That is just terrifying because human memory failed and, hangar norms took over. The FAA basically had to create a system where memory is replaced by an absolute permanent paper trail.
That's exactly why the rules are so strict. We operate under the Code of Federal Regulations, the CFR. Parts 43 and 91, they are the legal backbone of aviation safety. It dictates exactly how maintenance has to be recorded.
So let's break down some of these requirements, starting with airworthiness directives, or ADs.
Right, so if the FAA discovers an unsafe condition in an aircraft design, say a specific wing spar is prone to cracking after 3,000 hours of flight, they issue an airworthiness directive.
Okay.
And an AD is not a suggestion, it's not a polite recommendation. It is a legally enforceable rule. If your aircraft has an active, unaddressed AD, it is legally unairworthy. If you fly it, you are breaking federal law.
Wow. And then there's Form 337, right?
Yeah, Form 337. That's required anytime an aircraft undergoes a major repair or a major alteration.
Like what kind of alteration?
Like if you change the structural strength, the performance, the flight characteristics, you have to fill out a 337. It meticulously details the work performed, the approved data you used, and the signature of the inspector. One copy stays with the aircraft, and one goes straight to the FAA Aircraft Registration Branch to become part of the plane's permanent federal record.
But realistically, with so much paperwork, ADs, Form 337s, logbook entries, how can a modern mechanic strictly follow a manual written for an airframe designed in 1965? Half the original parts probably aren't even manufactured anymore. Do mechanics ever feel like they're just fixing paper instead of fixing airplanes?
I get that question a lot, especially from younger technicians just getting started. But you got to realize the paperwork is the airplane's memory.
It's memory. I like that.
Yeah, because aircraft change hands constantly across decades. A Cessna built in 1975 might have had 12 different owners and been maintained by 50 different mechanics by now. When I open that logbook, I am reading the medical history of the machine.
Right, you have to know what's been done to it.
Exactly. I need to know if a substitute part was legally approved and installed 30 years ago.
Yeah.
Maintaining a clean tail number, which means the logbooks are pristine and every AD is complied with, that's the pilot's best insurance policy. It's the only way to prove a plane isn't a ticking time bomb.
So you really need the history to predict the future of the airframe, especially since the fleet is aging rapidly. We're talking to high schoolers who might be listening, and the airplanes they'll be working on or flying are often 50 years old.
Oh, easily. We are routinely maintaining half-century-old aluminum. And aluminum fatigues over time. Every time a pressurized airplane climbs to altitude, the cabin expands slightly, kind of like a balloon.
And then it shrinks when it comes back down.
Right. And over thousands of cycles, that microflexing alters the molecular structure of the metal. It makes it harder and more brittle.
The FAA sources actually discuss damage tolerance evaluations, or DTE, for fatigue-critical structures to address this. But take me through a real-world scenario with one of these older airframes. You've got a pilot complaining about engine performance, and you suspect an issue with this 50-year-old aircraft. How do industry concepts, things the sources call mag drops, TBO, and NDT, how do those actually play out on the hangar floor?
Okay, let's walk through it. So the pilot tells me they did their pre-flight run-up and they had a bad mag drop.
Okay, what is a mag drop?
So aviation engines use magnetos, which are self-contained generators that provide electricity to the spark plugs. And each cylinder has 2 spark plugs for redundancy, powered by a left and a right magneto.
Got it. So a backup system.
Right. During a run-up before takeoff, the pilot isolates them. They run the engine on just the left mag, then just the right. If the engine RPM suddenly plummet during that check, that's a bad mag drop. It tells me one of those ignition systems is failing to fire efficiently.
So you pull the cowling off to investigate the magnetos?
I pull the cowling off, but I also look at the broader picture. The logbooks tell me this engine is fast approaching TBO.
Time between overhaul.
Exactly. The manufacturer sets a hard limit, maybe 2,000 flight hours. Reaching TBO doesn't mean the engine will suddenly explode today, but it means the internal metal components, the piston rings, the crankshaft journals, the bearings, they've physically worn down from millions of strokes and extreme thermal stress.
The tolerances just aren't there anymore.
Right. The clearances between the moving parts have widened way beyond factory specs.
The engine is quite literally grinding itself away on a microscopic level.
Exactly. So I know the engine is tired, which could be causing our combustion issues. But because it's a 50-year-old airframe, I also need to check the aluminum engine mount. That's the part holding that heavy, vibrating block of metal to the fuselage.
And a visual inspection isn't enough for that.
No, not at that age. I'll use NDT non-destructive testing. I might use an eddy current probe, which induces a magnetic field into the aluminum. If there is a microscopic fracture in the metal beneath the surface, it disrupts the magnetic field and my instrument picks it up, so I can find the fatigue before the mount actually snaps.
That is incredible. But what happens when the owner of that vintage aircraft decides they want to modernize? Say they want to rip out all the old analog dials and put in a state-of-the-art digital touchscreen.
Well, you can't just bolt a new computer into a certified aircraft. You need an STC, a supplemental type certificate.
Okay.
When an airplane is first built, it gets a type certificate from the FAA proving the original design is safe. An STC is a massive engineering approval process, proving that this new, specific modification is safe and compatible with this specific vintage aircraft.
Which just really sets up a massive contradiction in aviation right now. You get inside a vintage plane and you see a state-of-the-art glass cockpit digital screens, synthetic vision, like those Aviation panels mentioned in the FAA safety briefings. It literally looks like a spaceship.
Oh, they're beautiful panels.
But that high-tech brain is entirely dependent on ancient analog sensors, isn't it?
That's the irony. You can have a $20,000 digital display giving you real-time weather and traffic, but the computer doesn't magically know how fast the plane is flying or what altitude it's at. It relies on the pitot system.
Break down the physics of that system for us. How does it actually measure airspeed?
It relies on a metal tube, the pitot tube sticking out of the wing facing forward. It catches the ram air pressure from the plane's forward motion. Then there's a small static port on the side of the fuselage that measures the ambient, undisturbed air pressure outside.
Okay, so two different pressure readings.
Right. And the instruments calculate the differential between those two pressures to determine your airspeed and your altitude.
So if a mud dauber wasp crawls into that 50-year-old pitot tube on the wing and builds a nest,
Then the tube is blocked. The pressure differential drops to zero. Your state-of-the-art glass panel will confidently feed the pilot completely false airspeed data.
which can lead to a catastrophic stall.
Exactly. The digital brain is entirely at the mercy of the vintage analog sensors.
So a modern aviation mechanic has to be a master of two completely different worlds. You have to know how to buck solid rivets into sheet metal using techniques from World War II, and you have to know how to troubleshoot a software glitch in a digital air data computer.
You're bridging a 70-year technology gap every single day on the hangar floor.
With the aircraft becoming this complex hybrid of vintage metal and modern tech, who's going to fix them? We always hear about the pilot shortage in the news. Everyone talks about it. But the sources we have today suggest the mechanic shortage is a massive hidden crisis.
Oh, it's huge. My generation, the technicians who have been turning wrenches for 30 or 40 years, we're retiring in huge numbers right now. The industry is facing an incredible vacuum of talent, just as the general aviation fleet continues to fly and the commercial fleet is expanding.
The talent forecasts are genuinely staggering. Boeing's forecast predicts a global need for 710,000 new maintenance technicians by 2044. Yeah, that is nearly a 4% annual growth rate. And CAE projects 416,000 new AMTs will be needed just by 2034.
And because the demand is so astronomical, the aviation maintenance technician, the AMT, has become one of the most secure careers left out there.
And the Bureau of Labor Statistics data confirms that too. The median pay for aircraft mechanics and avionics technicians is hovering around $79,000 a year. But the top 10% of earners are making over $120,000 a year. And the Boeing data shows their mechanics averaging around $36 an hour.
And honestly, that is just the baseline. When you factor in overtime, specialized ratings, or moving into management and inspection roles, the earning potential just skyrockets. And another thing, these are highly transferable skills.
Really? Like where else?
Well, if you learn to maintain a turbine engine on a business jet, you can work on power generation turbines, high-end automotive or industrial robotics. The mechanical fundamentals are the same.
If the pay is there and the technology is this advanced, why is public perception still stuck on this outdated grease monkey caricature? You know, the guy covered in oil swinging a hammer.
Stereotypes always lag behind reality, I guess. Modern AMTs are highly trained mechanical diagnosticians. I mean, yes, you will get your hands dirty, you're going to smell like jet of fuel and hydraulic fluid.
Right.
But half your day is spent plugging a laptop into an engine's digital control unit, analyzing thousands of lines of flight data, and using predictive software to figure out when a component is going to fail before it actually breaks. It requires a massive amount of intellect.
It requires a really unusual blend of skills.
It does. It takes mechanical intuition, that gut feeling when a bolt just doesn't torque down right or an engine sounds a half step off its normal rhythm. But it also requires highly disciplined study. You got to read the manuals, understand the legal weight of the federal aviation regulations, and just deeply respect the laws of physics.
So if you're listening to this and you're the kind of person who takes things apart just to see how they work, if you want a career where your skills have a direct, visible impact on human life and safety, how do you actually get started?
You look into FAA-certificated aviation maintenance technician schools. You start studying for your airframe and power plant certificates. Look, there are a lot of jobs out there where you push paper around all day, and at the end of the week, you aren't really sure what you accomplished.
Yeah, a lot of jobs like that.
But aviation maintenance gives you this unmatched, gritty satisfaction. You stand on the tarmac, you wipe the grease off your hands, and you watch an airplane that you just brought back to life throttle up, lift off the runway, and disappear safely into the clouds. And, you put them there.
That's a pretty incredible feeling. Taking a step back and looking at the lifespan of these machines, it actually leaves us with an incredible philosophical question to ponder based on everything we've unpacked today.
Oh, yeah. What's that?
Well, think about that 50-year-old Cessna. Over the decades, one mechanic removes and replaces the engine when it hits TBO. Another mechanic patches its aluminum skin after fatigue sets in. Someone else uses an STC to swap out the old analog dials for a modern glass screen. And over time, every single wire, pulley, and rivet gets replaced. It's the classic ship of Theseus paradox, but for airplanes.
Oh, I see what you mean. If the mechanics have eventually replaced every single part of that machine to keep it airworthy.
Exactly. Is it still the same airplane that rolled off the factory floor 50 years ago? Or is it a completely new machine born entirely from the hands of the mechanics who kept it alive?
That is a great question. I mean, legally it's the same tail number, but physically, that's all us.
Something for you all to mull over next time you see a plane climbing into the sky. Thanks for taking this deep dive with us. Keep looking up, and we'll catch you on the next one.